Hi, everybody. I'm Michael Darling, and with me is my partner in crime.
Elias Lopez.
And we're going to present to you our paper that we read called Toward Software Defined VANet Architecture and Services.
We start by asking the question, why vehicular ad hoc networks, VNAs? Well, they have the potential to improve vehicle safety, road safety, enhance traffic and travel efficiency, make a car ride more convenient, add comfort for the driver and the passengers. And another thing that arose, well, more and more people use cars every day. There are a lot more cars on the road as the years go by. So these devices might enhance in a cluttered world might enhance the driving of everybody, might make the road safer for everybody, which is something that we're always looking to improve in our growing society. Continuing with our train of thought, why software defined SDN for short, vehicular ad networks? So we're adding something else to our VNA networks that we discussed before. Well, the challenges with the current VNA implementation without SDN or OpenFlow is that we have an unbalanced traffic among multi-path topology and inefficient network utilizations. Sometimes there are too many cars. In the real world, there will be too many cars in one specific location and not many cars at other locations, so our network will not be distributed evenly. Our network utilization will not be distributed equally. So we need to make these networks flexible in the flexible enough architecture for this vehicular application. That's where OpenFlow and SDN come in. So this brings us to the point of this paper. In this paper, they explore the architecture, operations, and benefits of software-defined VNA services and new functionalities that are supported by this. So what are vehicular ad hoc networks, VNAs? VNAs are networks that allow vehicles to communicate with each other, basically. This communication will allow the user the comfortability that we demonstrated in the previous slides. So how does this communication work? How does this network work? Well, we have vehicle-to-vehicle communication, vehicle-to-base station communication, and vehicle to a 4G LTE that will communicate vehicle data in the mobile broadband. So more open, it can get to various locations fast. And also the base station, which is shown with the blue arrows as well in our graphic, this shows the communication to have a base station. So in case there's something going on at that intersection, these base stations are usually around busier corners, busier blocks. So now we give a brief overview of what is a software-defined network with OpenFlow. Well, as we first start with our graphic on the left-hand side. SDN is the separation of the control plane and the data plane. As we can see here, the control plane makes the decisions of where the data should go and what paths they should take for faster communication. And the data just follows the paths that are given by the control plane. Well, where OpenFlow comes in is that we need to be able to communicate our control plane and our data plane. So that's the role of OpenFlow. As we can see in our right hand graphic, it demonstrates the basic functionality of OpenFlow. So now we will define an architecture with software-defined networking and VNA combined. As we can see in our graphic, it looks very similar to the graphic we presented before in 2 slides ago. The only difference is that we added an SDN controller that, as you can see in the graphic, controls the 4G LTE base station and the roadside base station. That is the communication this SDN controller has. So our SDN controller is the logical central intelligence of SDN-based VNA network. And it controls the network behavior of the entire system through the nodes it specifically controls. Then these nodes relate the information to the vehicle level or one level deeper through as well from the SDN controller. So to summarize this whole graphic and this paragraph, the SDN controller pretty much controls the entire structure or the entire network. So what in this SDN controller? As we saw in the previous picture, this SDN controller is pretty much the most important part of the network. And it is, as it contains the functionality of the OpenFlow enabled switch and the traditional OpenFlow networks. plus an additional intelligence to enable different modes of operation in Benet environments. So the SDN module is a combination of packet processing and the interface that accepts input from the separated control plane from our SDN. Each SDN wireless node has a local SDN agent, which functionality depends on what features are enabled on the SDN wireless node. So now we get into software-defined VNA operations overview. We will separate this into 3 different topics, and to be noted, this is not all the different operations. In this slide, we will talk about the central control mode. As we can see in the graphic, the SDN controller, like we stated before, just controls the entire network. And then at that point, all the operations are carried out to the individual nodes through the 4G LTE tower. So the SDN controller is more separated and more the outskirts of the network. So now we go to another realm, to the distributed control mode. So in this situation, the SDN controller, the main controller, as we can see in the graphic, will not have any contact with the other nodes. So all the operations and all the guidance of the data and the communication will take care of themselves by the SDN control mode nodes. So these are smaller nodes that already have the SDN ability on them, but they're more on the individual networks. They will not go to the master network as we see in the graphic. So for the hybrid control mode of this operations overview, is in this case the SDN main controller does not necessarily have control over all of the nodes. It can have full control or no control at all, or anywhere in the middle. So now it can relegate responsibility to the individual nodes closer to the vehicles or the vehicles themselves. So the decisions taking place all over the place, sometimes by the main SDN controller, sometimes not. The policies and everything gets handled individually or by the node. It's a combination of both. So now that we have given a architectural overview, we can get to talking about the benefits of software-defined Benet networks. So one of the benefits is that SDN allows us to have a specific path selection to make informed routing decisions. This will cause our data to travel a lot faster. Our network will not become unbalanced. If our SDN controller sees if something is occupying a lot of bandwidth, then it might do something to alter the routes so it can improve network utility and reduce congestion. Another benefit of this software-defined VNA network is that it allows us to have a frequency or channel selection. To an example, we can dynamically allocate a channel for emergencies and such things, and it can allocate channels for basically everything to make our routes, to make everything, to make our paths, to make our data travel faster, and to have efficient bandwidth throughout our network. So at the beginning of this PowerPoint, we described a problem where our network might become congested at some points, and at some points there might be no usage at all. So we might have too much allocation of too much resources in a specific spot that we don't need it. Well, SDN attempts to solve this problem in this VNA network, as it can decide where nodes don't need that much power and reduce the power to them, decrease the bandwidth. And in some cases, it can increase the bandwidth as there's too much sparsity of nodes. So at this point, our SDN VNA network will increase the power at some nodes and have better network usage where that sparsity occurs.
A principal use case for vehicle-to-vehicle communications is safety. An SDN VANet can augment previous V2V services by dynamically reserving frequency for high-priority communications. The SDN can adjust emergency frequencies and protocols based on current conditions. This allows for the prioritization of emergency traffic. SDN provides advantages over previous approaches for surveillance, since the SDN controller can dynamically insert flow rules to direct the data to one or multiple places, whereas in traditional architectures, the requester, such as a police car, had to send out a request for the data. This service would allow for abstract logical networks to be deployed over shared physical networks. Each flow defines radios or interfaces using different frequencies. If the frequencies are not identical, each flow is isolated, which thus creates a virtual network for each flow. There are different methods for providing the service. One would be to use different roadside units for different flows. Another method would utilize time slicing. For architecture evaluation, the authors use the NS3 network simulator. Therefore, they compare SDN-based VANet to the previous ad hoc approaches. The road network simulation was performed using the Simulation of Urban Mobility program called SUMO. Figure 10 compares the packet delivery ratio of the SDN architecture compared to DSDV, AODV, OLSR, and GPSR. We can see on the x-axis is node speed, on the y-axis is packet delivery ratio. The SDN approach outperforms all the ad hoc approaches. This figure shows the packet delivery ratio for a simulation similar to the previous figure. However, in this case, the authors are demonstrating the need for fallback mechanisms when SDN controller communication is lost. The time period between the dashed lines shows the communication loss. This demonstrates that a SDN VANet with a central control mode is dangerous without a fallback mechanism. This figure shows a simulation similar to the previous. However, in this case, GPSR is utilized as a fallback mechanism. When we lose the communication, the ratio is quickly restored, and once the controller communication is restored, SDN routing begins again. This figure shows dynamic transmission power control improves SDN packet delivery. The dashed line denotes the time when the SDN controller increases transmission power from 250 meters up to 400 meters. This illustrates that the increased range promotes better connectivity. The SDN controller can dynamically decide to adjust the power based on information from wireless nodes. The main points that can be drawn from this paper are the feasibility of a software-defined VANet by comparing SDN-based routing with traditional ad hoc routing protocols, how fallback mechanism is a key feature that must be provided to apply the SDN concept into mobile wireless scenarios, and transmission power adjustment as one of the possible services that could be provided by a software-defined VANet. More advanced scenarios than from those seen in the operations overview. Example, where only a subset of the nodes lose communication to the controller. SDN VANet architectures where the SDN controller transmits controller over P2P mode using Wi-Fi. Other features that might become available if this architecture is to be developed. And that's all, folks.